All right, listeners, buckle up because we're diving deep into thermal emission in radio astronomy.
Ooh, sounds exciting.
It is. It's a lecture by Dr. Hassan Abdallah from the Department of Astronomy and Meteorology at Omdurman Islamic University.
Okay.
And you know we love to take these deep dives, so we're going to break down this fascinating topic
All right.
and explore how heat radiation from space,
Heat radiation.
yeah, it reveals all these secrets about the universe.
To a cosmic heat sensor.
Exactly, like a cosmic heat sensor. And we've got his lecture and a slideshow, too,
Oh,
called Thermal Emission Mechanisms.
perfect.
Yeah, we'll use both. Okay, so starting with the basics.
Basics.
The slideshow defines thermal emission
Okay.
as radiation produced by matter in
You know what?
thermodynamic equilibrium.
Right. Think of it this way. Everything in the universe, even you, emits some level of heat radiation. It's just the amount and type of radiation that changes,
Okay,
depending on the object's temperature.
makes sense.
Yeah.
So a scorching star
Yes. Like
is
until
going to blast out way more intense radiation than, say, a cool, dusty nebula.
Exactly. And radio astronomers can detect and analyze these emissions to figure out an object's temperature, what it's made of, and even how it's moving.
That's incredible. I
How
mean,
good it is. It is.
it's amazing what we can learn
Yeah.
just from these emissions.
All right.
Okay, now the lecture and the slideshow focus on two main processes:
Two processes.
blackbody radiation and thermal bremsstrahlung.
Okay.
Let's tackle blackbody radiation first.
Sure.
So the slide defines a blackbody
All right.
as an idealized object
Idealized. Okay.
that absorbs all incident radiation and emits energy based solely on its temperature.
Like a perfect absorber and emitter.
Whoa.
Yeah.
So it's like a perfect absorber
Perfect. Yeah.
and emitter.
Precisely. It's a theoretical concept, but it helps us understand how objects in the real world
Okay,
emit thermal radiation.
gotcha. All right. The next slide, it shows Planck's law.
Planck's law.
Now,
Yeah.
this is where things can get a little complex,
Still complex.
but bear with us.
We'll get through it.
It's the equation that describes how much radiation
How much? Okay.
a black body emits at different frequencies or wavelengths, depending on its temperature.
The key takeaway here is that hotter objects emit more radiation.
Oh.
And that radiation peaks at shorter wavelengths. Think of a piece of metal heating up.
Yeah,
First it glows red, then orange, and eventually white
right.
as it gets hotter and hotter.
So the color's telling us something about its temperature.
Absolutely. And this applies to objects in space, too. A hot young star will emit most of its energy at shorter wavelengths, like blue or ultraviolet light,
Okay.
while a cooler object, like a dust cloud, will emit more of its energy at longer wavelengths, like infrared or radio waves.
So that's why we can't see certain things
Right.
with the naked eye.
Exactly.
Got it. Okay. The slide mentions the Rayleigh-Jeans law
Really, geez.
as an approximation of Planck's law for radio wavelengths.
Yeah. This approximation simplifies things for radio astronomers because it shows that at longer wavelengths, the energy emitted is directly proportional to the temperature.
So they can use this to directly relate the radio emission
Yes.
they're observing to the temperature of the object.
Right.
That's pretty handy.
Very handy.
All right.
What's next? The next slide introduces Wien's displacement law. It states that the peak wavelength of a black body's emission is inversely proportional to its temperature.
So the hotter the object,
Yeah,
the shorter the wavelength of its peak emission.
you got it. This explains why the sun, with a surface temperature of about 5,800 Kelvin, appears yellow to us, as it emits most of its energy in the visible light spectrum.
That makes sense. The final blackbody law on this slide is the Stefan-Boltzmann law.
Stefan Boltzmann, yeah.
This one describes the total energy radiated by a blackbody.
This law states that the total energy emitted is proportional to the fourth power of its temperature. This means that a small change in temperature can lead to a massive change in the energy radiated.
Wow, that's a powerful relationship.
It is. It is.
You can see how even slight temperature variations in space can have huge impacts
Yes,
on the energy we observe, right?
exactly.
Okay, let's move on to the example on the next slide.
Okay, the example.
It shows the calculation of solar flux density at 1 gigahertz.
All right. Before we dive into the numbers, let's clarify what flux density means. Think of it like the strength of a radio signal. It tells us how much energy we receive from a source per unit area and per unit frequency.
Okay, so it's like
Yeah,
how strong the signal is.
exactly.
Okay, got it. So in this example, We're trying to calculate how much radio energy we'd receive from the sun
Yes.
at a specific frequency, 1 gigahertz,
1 gigahertz.
if we were observing it from a distance of 1 parsec.
That's right. Dr. Abdallah uses the Rayleigh-Jeans approximation of Planck's law here because we're dealing with radio wavelengths. The calculation involves plugging in the sun's temperature, radius, and distance.
Okay. And after all the calculations, what does Dr. Abdallah find?
The sun's flux density at 1 gigahertz, when observed from 1 parsec away, turns out to be incredibly small, about 0.3 microjanskis.
Wow, that's tiny.
It is tiny, yeah.
A Jansky is a unit of spectral flux density.
Right.
And 0.3 microjanskis is a minuscule amount of energy.
Right. This highlights the incredible sensitivity needed in radio astronomy to detect such faint signals from distant objects.
Really underscores the vast distances involved in astronomy.
It does.
I mean, even our sun, this giant ball of burning gas,
I know.
looks like a mere whisper on a radio from a distance.
Amazing.
Okay, ready to move on to the next process.
Absolutely. Let's dive into thermal Bremsstrahlung, our next topic on the slide.
Bremsstrahlung. It sounds a little intimidating,
A little intimidating.
but I'm ready to tackle it.
Don't worry, it's not as scary as it sounds. Imagine zooming into a plasma, which is a superheated state of matter where atoms have been stripped of some of their electrons, creating a mix of charged particles.
Oh.
So instead of neat little atoms, you have electrons and ions zipping around in a chaotic dance.
So it's like
Yeah.
instead of just atoms,
You've got all these particles.
electrons and ions just like
Yeah.
zipping around.
Exactly. Now, when an electron gets close to an ion, it gets deflected by the ion's electric field, causing it to decelerate and lose some energy. That lost energy is emitted as electromagnetic radiation. That's Bremsstrahlung.
Oh.
Yeah.
So it's like a cosmic braking system.
It is, it is.
Where the energy lost
Yeah,
by the electron is released as light.
that's a great way to put it. And this radiation, unlike blackbody radiation, produces a continuous spectrum.
Meaning?
It emits radiation across a wide range of frequencies, making it ideal for studying the overall properties of hot gas clouds. Without getting bogged down in analyzing individual spectral lines from specific atoms.
So it's not like
Right.
discrete.
Oh, that's great. Yeah.
It's a wide range.
A whole range.
Okay. The next slide lists some key factors affecting Bremsstrahlung.
All right.
It says the amount of emission depends on things like the density and temperature of the plasma.
That's right. The hotter and denser the plasma, the more frequent the interactions between electrons and ions, and the stronger the Bremsstrahlung emission.
Okay, so it's kind of like a crowded dance floor.
It is.
The more people dancing and bumping into each other, the more chaotic energy is released.
I love that analogy.
That's a great analogy.
It is. And that's why thermal Bremsstrahlung is a powerful tool for studying ionized regions in space,
Yeah.
like those found around hot young stars.
Okay. Makes sense. Wow, we've covered a lot of ground here.
We have.
We learned about blackbody radiation, the baseline for understanding how objects emit heat,
Yeah.
and then we dove into thermal Bremsstrahlung,
Thermal Bremsstrahlung.
this fascinating process occurring in plasmas.
Fascinating indeed.
Yeah.
Both processes provide valuable insights into the workings of the universe. And in the next part of our deep dive, we'll explore some specific examples of how they manifest in various cosmic objects.
Oh, I am.
To be good.
I'm already hooked. I can't wait to see how all of this plays out in the real universe.
Me too. All right, so are you ready to see these processes in action?
Oh, absolutely. I'm ready for some cosmic fireworks.
You got it. Our first stop is the cosmic microwave background, or CMB. It's the faint afterglow of the Big Bang, this whisper of light that's been traveling through space for almost 14 billion years.
Wow. So we're talking about like light from the very beginning of the universe.
Exactly. It's like a baby picture of the cosmos. The slide calls it remnant radiation from the hot, dense early universe. About 380,000 years after the Big Bang, things cooled down enough for protons and electrons to, get together.
Like a cosmic meet cute.
Yeah, kinda. They formed neutral hydrogen atoms.
So before that, was it just this big opaque soup?
Pretty much. Light couldn't travel freely. But as the universe expanded and cooled, it became transparent. And that first light, the CMB, was released.
And it follows a near-perfect black-body spectrum, right? That's what the graph on the slide shows.
It's incredible, isn't it? A stunning confirmation of the Big Bang theory. The CMB's temperature is a frigid 2.7 Kelvin, telling us how much the universe has cooled and expanded since its fiery birth.
That's crazy cold.
It is, but there's something even cooler, literally.
Okay, I'm intrigued.
Within the CMB, there are these tiny temperature fluctuations, little variations from place to
So
place.
it's not perfectly uniform.
Right. These fluctuations, we're talking millionths of a degree, they represent tiny differences in density and temperature in the very early universe.
And what do those differences do?
They acted as seeds, gravitational seeds for everything we see today. Galaxies, clusters of galaxies, even the cosmic web that connects it all.
Wow. So we're seeing the blueprint of the universe, basically.
Right.
Okay. From the grand scale of the CMB, let's zoom in, get a little closer to home. How about stars, those HII regions, those stellar nurseries?
Love it. The slide shows a fantastic image of the Orion Nebula, a perfect example of an HII region. All those colors, that hot ionized gas.
It's one of the most beautiful sights in the sky, for sure. The lecture says that these HII regions are powered by these massive hot stars.
Exactly. These young, energetic stars blast out huge amounts of ultraviolet radiation, which ionizes the surrounding hydrogen gas. And that creates a plasma.
So that's why it glows so brightly, right?
Yeah.
The plasma.
You got it. And part of that glow comes from, you guessed it, thermal Bremsstrahlung. Those chaotic interactions between the electrons and ions in that hot plasma, they release energy as light.
So it's not just the stars themselves, it's this whole chain reaction.
Exactly. And by studying the radio emission from HI regions, specifically the Bremsstrahlung, astronomers can learn so much.
Like what? What kind of things can they figure out?
Well, they can measure the gas temperature, which is typically around 10,000 Kelvin, much hotter than our sun's surface. And they can measure the electron density, too, which tells them how many free electrons are zipping around in that plasma.
And that helps them understand how stars are born, how they evolve.
Exactly. It's like putting together a cosmic puzzle, where each piece of data brings us closer to the big picture of star formation. Now, ready for something a little less flashy, but equally important?
Okay, hit me.
Let's talk about dust.
Dust. Seriously.
Yeah. It's not as glamorous as stars and nebulas, I know, but dust plays a huge role in galaxies. The slide explains how dust grains, tiny particles of carbon, silicates, things like that, absorb starlight
Okay.
and re-emit it thermally, but at longer wavelength.
So they're like cosmic middlemen, taking starlight and turning it into, what, infrared and submillimeter radiation.
Perfect analogy. And this dust emission, it's gold to astronomers. They can map out the distribution of dust in galaxies, trace the structure of those beautiful spiral arms. They can even estimate star formation rates.
Wow. So dust is actually really important.
It is. Think about the Andromeda Galaxy, our neighbor. This slide shows an infrared image of it. Look at those glowing dust lanes tracing out the spiral arms. It highlights exactly where stars are being born.
It's incredible to think that we've gone from the entire universe, the CMB, to these star-forming regions, and now even the dust between the stars. But it's all connected by the same physics, right?
Exactly. It's pretty amazing, right?
Yeah.
The elegance and universality of those laws that govern the universe. Now, for our final stop, we're bringing things a little closer to home. Let's talk about planets and moons.
Ooh, planets.
Yeah.
I've always been fascinated by the idea that even planets, even these smaller, cooler objects, emit heat radiation.
Remember the Stefan Boltzmann law? It says any object with the temperature above absolute zero emits thermal radiation. Planets are no exception.
So even though planets are much cooler than stars, they still give off a heat glow,
A
right?
faint one, yeah. And because they're cooler, their emissions peak at longer wavelengths, usually in the infrared.
So it's like they're whispering in infrared instead of shouting in visible light like stars do.
I love that. And those whispers, they tell us a lot. Astronomers can determine a planet's surface temperature, figure out what its atmosphere is made of, even get clues about its internal activity.
Wait, so you can tell what a planet's atmosphere is made of just from its infrared light?
Yeah.
Ow.
It's all about spectroscopy. Different gases absorb and emit infrared radiation at very specific wavelengths, like a fingerprint. So by analyzing the infrared light coming from a planet, astronomers can match those fingerprints and identify the gases.
It's like they're reading the planet's chemical barcode.
Exactly. And sometimes we find some pretty surprising things. Look at Jupiter. Its infrared glow reveals that it's not just reflecting sunlight, it's actually generating its own internal heat.
So Jupiter's like a mini star, in a way.
Not a star, exactly, but it definitely has its own internal heat engine. likely from gravitational contraction and that slow cooling of its massive core.
Wow. What about moons? I remember the lecturer mentioned Europa, one of Jupiter's moons.
Ah, Europa. It's really captured people's imaginations because those infrared emissions hint at the possibility of a vast ocean beneath its icy surface.
Hold on, an ocean underneath all that ice. How's that even possible so far from the sun?
Well, tidal forces from Jupiter and its other moons generate heat inside Europa, keeping that water liquid underneath the ice.
Incredible. And liquid water. That makes you think of.
Life, you got it. That potential for a habitable environment is why Europa is a prime target in the search for life beyond Earth.
Wow. From the echoes of the Big Bang to the possibility of life on an icy moon, this has been an amazing journey.
It has, hasn't it? But I think it shows something really profound.
What's that?
Thermal emission, it's more than just a physics process. It's like a cosmic language. It's how the universe communicates its secrets to us. And by learning to listen, we can unravel those mysteries, understand our place in this grand scheme of things.
That was quite a journey. From the universe's first light to hidden oceans on icy moons, all thanks to thermal emission.
It really shows you, doesn't it, how much we can learn just from heat radiation.
Yeah, it's like this hidden language of the cosmos.
Exactly.
So let's recap. We started with blackbody radiation, the idea that anything with a temperature above absolute zero emits thermal radiation.
Right. And the hotter it is, the more intense the radiation, shorter the wavelength.
Right. And we saw how Planck's law helps us calculate all that, determine an object's temperature and energy output.
And then there's thermal Bremsstrahlung, that process where charged particles in those hot plasmas, they interact.
Yeah.
And emit radiation, creating this continuous spectrum of light.
And we saw how these two processes, they play out on such a grand scale. The cosmic microwave background, those star-forming regions.
The dust in galaxies, even planets and moons.
It's amazing how it all ties together. From the biggest scales to the smallest, it's all connected.
It really highlights the elegance of physics, doesn't it?
It does.
Yes.
But before we wrap up, something's been on my mind. We've talked about how thermal emission helps us understand these distant objects.
Right.
But what if we turn those telescopes back towards Earth?
Ah, that's an interesting thought. What could we learn about ourselves?
Right. I mean, could we see, like, heat distribution across the continents or track ocean currents? Could we even see volcanic activity?
Maybe. We might even be able to analyze the composition of our atmosphere, track cloud cover, even monitor climate change.
It'd be like seeing ourselves in a cosmic mirror.
It would. A whole new perspective on our own planet.
Wow. This has been an incredible deep dive. So many mind-blowing insights.
I know. It's amazing what we can learn when we just, listen to the universe.
It really is. So to all our listeners out there, keep exploring, keep asking questions. The universe is full of mysteries waiting to be uncovered, and who knows what amazing things we'll find next. All right, listeners, buckle up, because we're diving deep into thermal emission in radio astronomy.
Ooh, sounds exciting.